Hey, welcome back. Today we're going to learn how to difference between vectors and scalars, how to break a vector into the x and y components, how to construct a resultant vector graphically, and how to calculate a resultant vector algebraically. So we got a lot on tap for today. Now this is review for you. The scalar is going to show no magnitude, shows the magnitude, but it's not going to have direction. So examples of this could be 30 meters per second or 10 meters per second. Could be 30 meters or 10 meters. A vector is going to show magnitude and direction. So, for example, we could have 30 meters per second east and 10 meters per second west. The arrow should, the length of the arrow should indicate the magnitude. And that's why if you look on here, you'll see that the one going to the east is approximately 3 times the size of the one going to the west. All right, adding vectors. So graphically, the way we want to do this is we want to draw tip to tail. We're going to use a scale, and we want to measure resultant using the length and report the angle as well. Report the length and the angle of the resultant. So on here we had 2 vectors. Here was a vector and here was another vector that we added together, and the red one here was the resultant. So this could be for like displacement. We want so many meters east and then so many meters at an angle. There'd be an angle here in the northeast direction. What is their displacement? Well, the displacement then would be the resultant. How far are they from where they started? Okay, and this one says the roller coaster moves 100 meters horizontally, then travels 40 meters at an angle of 30 degrees above the horizontal. What is the displacement from its starting point? So I'm going to use my scale. I'm going to use every centimeter equals 10 meters. So 1 centimeter equals 10 meters. Which means I'm going to have to draw a vector here that is 10 centimeters long. Let's hope it all fits on here. So there's my 10 centimeters. So I just represented 100 meters horizontally and then travels 40 meters at an angle of 30 degrees. So what you can't see here is I'm putting my, I think it's called a protractor. And I'm putting a little mark over here where 40 degrees would be. So approximately, if I were to continue this, and then this right here is my 40 degrees, what is the displacement? So let's measure this out. 40 meters, so it'd be 4 centimeters. All takes time. Then the question, so I want tip to tail. I didn't do very good right here. How about we make it? So this is my tip, this is my tail. Tip to tail, this is another tip. Now it's drawing that resultant. My resultant goes from where we started to where we finished. And I got this to be 13 centimeters, so that'd be 100. Gotta go back to my draw feature here. So this right here is 130 meters, and when I measured it, I got 11 degrees. So I would say 11 degrees, and I'm going to say northeast, because it's pointing in the northeast quadrant. So there we go. That's how we add them up. Hopefully that was pretty easy for you. Here's one for you guys to do on your own. I'm not going to give you the answer right now, but it says a dog's moving 10 meters east, travels 4 meters at an angle of 20 degrees north of east. What is the displacement from its starting point? So that's one for you guys to work on. Now the next thing we're going to do here is breaking into x and y components. So we just showed you how to add up vectors graphically. Now we're going to do some work here with algebraically breaking vectors into their x and y components. So what do we mean by that? So here is a velocity vector. I've given it to you as 7 meters per second at 30 degrees northeast. Well, what does that mean? What that means is that this has both x and y components. I can break this down into its x component, meaning, yes, it's going up and to the right, but how much of that is just going to the right? And typically, so this is what we'd call the x component. And then how much is it going just up? How fast is it going just up? Alright, so in this case, we're going to use our trig ratios. I've went ahead here now and drawn in the x component, so how much of this is going to the right. I've drawn in the y component, telling us how much of this 7 meters per second at 30 degrees northeast is going in the up direction. So again, we're trying to break this up into its x and y components. How fast is it going forward? How fast is it going just up? Well, if I use my trig ratios, opposite given the hypotenuse is the sine function. The sine theta equals opposite over hypotenuse. I'm going to change opposite to the y because that's what I want. So, and if I multiply both sides by h, we get h, or the hypotenuse, times the sine of theta equals our y component. That's very important. So in this case, our hypotenuse is 7. Sine of 30 equals our y component. Let's find our x component. To do that, I have my adjacent and my hypotenuse. So what I'm going to use is the cosine function. The cosine of theta equals the adjacent over the hypotenuse, but I don't want the adjacent, I want the x component, so I'm going to change this to x over h. Do the exact same thing, multiply both sides by h, and we get h cosine of theta equals our x component. Or we could say, in this case, 7 cosine of 30 equals x. Another important equation right there. Now, a lot of times you kids coming out of calculus have it set to radians. Make sure your calculator is always in degrees. Alright, so what I just found here then, for those of you that wanted the numbers, y was equal to 3.5 meters per second and x was equal to 6.1 meters per second. Alright, so here's a practice problem of how we would add vectors by using components. A boy runs 25 degrees northeast, so here's 25 degrees, or 25, sorry, backtrack that. My own reading skills weren't very good. 9 meters per second at 25 degrees northeast, and then here it's the wind's blowing 7 meters per second at 30 degrees southeast. So let's break this into its x and y components. I've already written in the x and y, so this first one I'm going to say x then equals 9, because that's my hypotenuse, cosine 25. This one here is going to be y equals 9 sine 25 degrees. This is going to be x equals 7 cosine 30 degrees. And this is going to be y equals 7 sine of 30 degrees. So what I've done is I've gone ahead and broken these all up into their x and y components here. Found out what they would be, punched them in my calculator, and now I'm just going to add the ones that are the same. X's, I'm going to add my two x's together, 8.1 and 6.1. So my overall x resultant, this resultant that would be going right through here, his overall x speed is equal to 14.2 meters per second. The y component, well, I've got a positive 3.8 here and a negative 3.5 here, so his y component would be equal to 0.3 meters per second. So what that tells us here is, even though the boy can only run 8.1 meters per second on his own in the x direction because of the wind, that's where they come up with these wind-aided results, he's actually running at 14.2 meters per second. Alright, here's one of the last things we're going to go over here. Hints to solve projectile problems. Projectile meaning things that have both x and y components. Draw a picture. Alright, draw a picture. And that's going to be usually drawing the vectors of what they give you. Identify all the givens. Alright, what information are they giving you along with the vectors? Break it down into its x and y components. Usually that's going to be speed. Sometimes we'll deal with displacement. And then use kinematic equations. Alright, so let's discuss what we did here today. We learned about the difference between vectors and scalars. We talked about characteristics of vectors, how to construct a resultant vector, and how to calculate a resultant vector algebraically. Well, if you have any questions on this, and whether you do or not, we're still going to talk about it. I'll see you guys on the flip flop. I will catch you guys on the flip side.